Hey guys, so in this course in Algebra 2, you have already looked at lots of different types of functions and what their graphs look like. We call that linear functions are lines, quadratic functions are parabolas, cube root functions are sideway s's, square root functions look like a square root, and absolute value functions are v's, exponential functions either go up or down, approaching an invisible horizontal line that we call an asymptote, etc. So today we're going to look at one last type of function that we're going to learn this year in Algebra 2, and it's the rational function. For the past week or so, you've been working with rational expressions, which are really just fractions, right, with variables in them, because a rational number is a fraction. So a rational function is just a function that is in the form of a fraction where the numerator and denominator are polynomials. And the simplest rational function that we're going to look at is y, or f of x, equals 1 over x. So what does this graph look like? What kind of shape does it have compared to all of our other parent functions? We're going to go ahead and graph the parent functions, and we're going to do a little bit of transformations. So normally when we make a table for parent functions, we start with -2, -1, 0, 1, 2, right? Except for the square root functions where we can't put in the negative. So let's just start there and see what happens. Let's start with -2. Okay, so 1 divided by, according to my function rule, 1 divided by -2, that's just going to give me -1/2, right? So I'm going to graph that right here. -2, -1/2. Okay, what about -1? 1 divided by -1 is just going to give me -1. Okay, so -1 right here. Okay, so now we kind of have a little problem when we try to put in 0, because we know that we cannot divide by 0 in math. So 1 divided by 0 is going to be undefined. So we don't have a point there, which means that there is never going to be a point. There's no way that there can be a point at x equals 0. So I'm going to draw this little invisible vertical line that tells me, okay, there can't be any points here. All right, let's see what happens at 1. Okay, 1 is good. 1 divided by 1, if x is 1, 1 over 1 is just 1. And 2 is good, right? 1 over 2 is 1/2. Okay, so I'm going to graph that. 1, 1, 2, 1/2. Let's keep going and see what happens, because I only have 4 points here. Okay, and I don't really know how to connect them yet. How about 3? That would be 1/3. Okay, and if I go all the way, 4 would be 1/4. And then if I go all the way to the right to 10, this is going to give me 1/10. So notice that as x gets larger and larger, your y values get smaller and smaller, and it gets closer and closer to 0, but it actually never hits 0, right? If I pick 1,000 for x, y will be 1 over 1,000, which is be so close to y equals 0, but still not quite there yet. And so there is, in fact, so this is what happens to my graph on the right side. Gets closer and closer to the x-axis, but never touches it. And if I pick 1/2 for x, 1 divided by 1/2, keep change flip, is going to give me 2. So at 1/2, it's actually at 2. And what the shape of this function kind of looks like, it looks like it's got like 2 branches that gets closer and closer to these invisible horizontal and vertical lines that we call asymptotes. So there is an invisible horizontal line at y equals 0 and an invisible vertical line at x equals 0 that my graph gets closer and closer to on either side, but never quite approach it. And same thing with the negatives. It's going to get closer and closer to my 2 asymptotes, but never quite touch it. And so this is what the graph of a rational function typically looks like. You've got both a horizontal and vertical asymptote. They're invisible horizontal vertical lines that my graph gets closer and closer to, but never touch or cross it. And then you've got 2 parts of the graph. So the asymptotes kind of act as a divider and as a border to separate your graph into 2 parts. So a rational function is just an expression written in the form f of x equals n over x over d over x, where the numerator, so basically a fraction, where the numerator and denominator are both polynomials. And because we have a fraction, we want to make sure that the denominator can never be equal to 0. And that's why at 0 it is undefined. Okay? In this case, whenever we have rational functions, we're going to have horizontal and vertical asymptotes, which are the invisible lines that a graph approaches but never quite reach. And typically for the parent function, y equals 1 over x, your x and y axes serve as those asymptotes. So when we apply transformations and we shift our graphs to the left, to the right, up or down, all we have to do is shift the x and y axis, and that will identify our kind of boundary lines and our borders for our graph, right? So let's take a look at an example. Okay, so example 1, we're going to graph the following function, which looks very similar to the parent function. So if we think about the parent function is y equals 1 over x, and then let's think about what we know about transformations. The only difference here is this plus 2. That is in the denominator where the x is, right? Remember we said adding and subtracting, the transformations, adding and subtracting are your shifts, shifting left, right, up, or down. Since it's in the denominator of my fraction where the x is, I know it's going to be a horizontal shift applied to the x. And remember we had said, when we learned transformations, that everything applied to the x is counterintuitive, so it's the opposite. So it says x plus 2, okay, which actually means we're going to move our graph to the left 2 units. And instead of making a table every time, I'm going to show you a little shortcut, because I know in my parent function that my x and y axes are my asymptotes. So all I have to do is move my x and y axes if I need to, according to the transformations, right? So if I'm shifting every point on my graph to the left 2, then my y-axis is just going to move over 2. Here it is, my new y-axis, which is my asymptote, my invisible vertical line. Okay, and then I don't have to move up or down, so my x-axis can stay here, not moving it up or down, just moving my whole graph to the left 2 units, and then everything else stays the same. So treat it as if it's your new x and y axis, and use our 2 points, one on each side of the vertical asymptote that we had graphed before. So we had said 1, 1 was a point, right? If x is 1, y is 1. 1 divided by 1 is 1. So here is 1.11. Okay, treating these as my new x and y axis, that point right there is 1, 1. And then negative 1 is another point. And then I just have to, I did an orange, so I'll do an orange. I just have to plot 1 point on either side to the left and to the right of the vertical asymptote, and then kind of draw our 2 branches. They kind of look like branches that gets closer and closer to my asymptote. And then same thing on the left here. And then that's it. So very similar to the graph that I had just made, except everything is shifted to the left too, according to my transformation. Now I identify the domain, or vertical and horizontal asymptote. Let's identify those first. I have a vertical asymptote. That's a vertical line at x equals negative 2. That's my invisible vertical line that my graph approaches. And then I have a horizontal asymptote at just y equals 0. That didn't move. That's right here. Okay, so basically my 2 boundary lines is what it is. Okay, and then my domain. So this is the domain for the entire graph. Remember domain, we read our graph from left to right. So starting on the left, it seems like the arrows indicate that my graph keeps going to the left. So I'm going to start at negative infinity on the left. Okay, and as I move to the right, looks like there's a little gap here because we said x cannot be negative 2. Otherwise, we would have a problem with the denominator of being 0. So this dotted line tells me that x cannot be negative 2. So from negative infinity to negative 2, x could be any point between negative infinity and negative 2. There's a little gap at negative 2, so I'm going to put union. Okay, and we do not include negative 2 because x cannot be negative 2. X could also be anything between negative 2 and on, right? To the right. From negative infinity to negative 2, and then starting at negative 2, x could be any point to the right. And so that's negative 2 to infinity, again, not including negative 2. Now my range, I'm going to look up my graph from bottom to top. So again, looking at my graph on the bottom, the arrow keeps going down. So I'm going to start at negative infinity on the bottom, and I'm going to move up, and it looks like I have to stop at 0 because there's a gap at 0, so not include 0. And then union from 0 to infinity, again not including 0. So basically, my domain is negative infinity to infinity, everything except negative 2. And that's why we have to separate it at negative 2. And my range is, again, basically from negative infinity to infinity, except right here, where there's no point at y equals 0. And so we have to put a little gap there, okay? And because there are two sections, we put the union symbol to kind of connect them. Okay, one last example, very similar, except now my parent, remember my parent is y equals 1 over x, so let's identify what the changes are. It looks like I subtracted 3 from the x, but we know that's counterintuitive, so I actually went 3 units to the right instead of left. Okay, and then we've got also this plus 4 right there. That is not in the denominator where the x is. So we know that's actually applied to the y if it's not applied to the x. And everything applied to the y is intuitive, so it just means 4 up. So now we are shifting our x and y axes, which are also our asymptotes, to the right 3. Okay, so here's my new y-axis, or my vertical asymptote, and up 4. So here's my new x-axis, which is my horizontal asymptote. Okay, so treating these as our new x and y axes, we're going to go ahead and plot our 2 points, one to the left and one to the right of my vertical asymptote. So we've got 0, 0 would be right here. That would be your new origin, right? And then this would be 1, 1. Oops. 1, 1 would be right here. Negative 1, 1 would be right here. And then we just have to draw the rest of our graph. Approaching the asymptote. Same thing over here. Approaching the asymptotes. Okay, so we have a vertical asymptote at x equals 3. That's our vertical invisible line that my graph approaches, and a horizontal asymptote at y equals 4. Right here, which is where my new x and y axis got shifted to. And then my whole graph shifts with it, okay? And then my domain and range, I've got domain starting on the left at negative infinity. And as I move from left to right, there's a gap at 3 that x cannot be. And then union from 3 to infinity. And for my range, starting on the bottom at negative infinity, as I move up, there's a gap at 4 that y cannot be. And then from 4 to infinity, that is your range. So as you do your practice problems, follow the same exact process. Start by identifying the transformation that will tell you how to shift your x and y axes, which are also your asymptotes, up, down, left, right. Remember, what's applied to the x is always counterintuitive, so it's the opposite. And then once you shifted your asymptotes, you can graph a point on the left, a point on the right using 1, 1. and -1, -1, and then draw out your two branches and identify your domain and range.